to C for all n greater than or equal to 1. A numbers are rational numbers, then we say that positively bounded away from 0 means after some time, after some integer, all of them are positive. That's what it says. The sequence is negatively bounded away from 0 if and only if we have a negative rational, negative C less than 0, such that A less than or equal to minus C for all n greater than or equal to 1. In particular, this sequence is entirely negative, he says. The sequence, the now 1.1, 1.01, etc. is positively bounded away from 0. All terms are greater than 1. No? I mean, you can see it right away. The sequence minus 1.1, minus 1.01, etc. is negatively bounded away from 0 because all of them are less than or equal to, for instance, minus 1. The sequence 1 minus 1 and so on is bounded away from 0 but is neither positively bounded away from 0 or negatively bounded away from 0. So they are clear. It is clear that any sequence which is positively or negatively bounded away from 0 is bounded away from 0. That is very clear. Also, a sequence cannot be both positively bounded away from 0 and negatively bounded away from 0 at the same time. I mean, no real number will be positive and negative. It's a trichotomy in I. It is positive, 0, negative, one of them. Definition 4.3, a real number x is said to be positive if and only if my throat is bad. I don't know why. If and only if it can be written as the formal limit of an for some Cauchy sequence which is positively bounded away from 0. That's how we say x is positive. If it can be written as, you can find a sequence A, all of them are positive. Not only that, it is bounded away from 0. If you can find such a one, then we say for some Cauchy sequence which is positively bounded away from 0. So very important, the number x is said to be positive. How does we say? If it is a formal limit of sequence A for some Cauchy sequence which is positively bounded away from 0, same way he is saying x is said to be negative if and only if it can be written as x is equal to formal limit of A for some sequence A which is negatively bounded away from 0. So these are two good definitions from his style. Let's see, basic properties of positive reals. For every real number x, exactly one of the following three statements is true. X is 0, x is positive, x is negative. A real number x is negative if and only if minus x is positive. If x and y are positive, then so are x plus y and xy. So it is an exercise, so I will not do it now. Note that if q is a positive rational number, then the Cauchy sequence q is positively bounded away from 0 and hence formal limit of q is a positive real number. Thus the notion of positivity for rationals is consistent with that of reals. Similarly, if it is, you can see now if you can find the sequence of rational numbers bounded away from 0, formal limit is said to be positive. So, since if you take a positive rational number, again according to this definition also, it is positive. That's what it says. Thus the notion of positivity for real rationals is consistent with that of reals. Similarly, the notion of negativity for rationals is consistent with that for reals. Once we have defined positive negative real numbers, we can define absolute value and order. So as far as analysis is concerned, order is the important thing. Other things, did you check with this late Putta?
Yeah, he didn't reply.
Yeah. So he came to lunch, have his that's enough for him.
He might come for the lunch in candy.
Candy lunch, yeah. So let x be a real number. We define the absolute value of x to equal to if x is positive or negative. If equals x if x is positive, negative x when x is negative, 0 when x is 0. That's the normal definition. Definition 5.4.6, ordering of the real numbers. Let x and y be real numbers. We say that x is greater than y and write x strictly greater than y if x minus y is supposed to be a real number. And x less than y if and only if over there if over here if and only if. That's not good. If and only if x minus is a negative real number. We define x greater than or equal to y if is x greater than y or x is equal to y, and similarly. So less than or equal. Comparing this with the definition of order on the rationals from definition 4.28, we see that order on the reals is consistent with the order of the rationals. That's sure. That is, if two rational numbers q dash are such that q is less than q dash in the rational number system, then q is still less than q dash in the real number system, because you have q dash. And similarly for greater than. In the same way, we see that the definition of absolute value given here is consistent with that in definition 4.3.1. So I cannot remember definition 4.3.1 anyway. That is one little problem with this book. He is referring to previous. He has to refer, but the method is not friendly with us. That's the thing. All the claims in proposition 4.2.9 which held for rationals continue to hold for real numbers. He says, there are 8 or 9 of them, I can remember. Proof, we just prove of the one of the claims and leave the rest to exercise 5.4.2. Suppose we have x less than y and z is supposed to be real, and want to conclude that x is less than y is we just prove one of the claims and leave the rest to exercise 5.4.2. Suppose we have x less than y and z is a positive real, okay, and want to conclude that x is less than y is okay. Since x less than y, y minus x is positive by definition. That's how we define less than. Hence, by proposition 5.4.4, we have y minus x is positive, z is also positive. Then we have y minus x times z is equal to y z minus x z. Y minus x times z is positive. No, it's not clear. There are many places. Can you see what I'm saying?
Yeah. They can probably mention that.
Doesn't really mean. So x is less than y is it? So it's proof. The way it's said is not great. Proposition, as an application of these propositions, we prove let x be a real number, then x to the minus 1 is also positive. Also, if y is another positive real number and x greater than y, then x inverse less than y inverse. So let's go through the proof. Doesn't matter. Let x be positive. Since x to the minus 1 is equal to 1, the real number x inverse cannot be 0 because x times 0 is equal to 0. 1 and 0 are not equal. Though he says 1 and 0 are not equal, was it proved?
No, he just uses.
He's just saying, that's again not reliable. Usually in other real number systems,
No, 1 is equal to 0 plus plus. So 0 is not the succession now.
So good that you pointed out it. So this system is difficult for us.
Hard to work with.
Yeah. Also from proportion 5.4.2, it is easy to see that the positive number times a negative number is negative. This shows that x inverse cannot be negative because we know that 1 is positive. If by any chance x minus were negative, then x times x minus, since x is positive, it must be negative. So that's a contradiction. That's why proportion 5.4.4, the only possibility left is that x inverse is positive. He showed that x inverse cannot be 0. He showed that x inverse cannot be negative. And only thing left over is x inverse is positive. Now let y be positive as well. Then so x inverse and y inverse are also positive. No, that's what we have proved. No? If x inverse greater than or equal to y inverse by any chance, then by proposition 5.4.7 over there, that we assume without doing the homework, if x might, then by 5.4.7, x times x inverse greater than y times x inverse. Next, last one is clear, y times x inverse greater than or equal to y times y inverse.
X is greater than y now, so
But
we
have we proved it?
no, it is proposition. So he supposed that x is greater than y.
Proposition 5.4.7. Yeah, of course we can prove it, but have we proved it? That's what I'm asking.
No, the above one. Proposition 5.4.7 is in on the top on the screen.
Oh, but it is 4.29 to 9 here, no? Let's go and see whether we have proved it. 4.2.9. 2.4, 2.8, 2.9. It says trichotomy holds for less than, greater than this. Order is antisymmetric, that's true. Order is transitive, that is true. Addition, last one. If x less than y and z is a positive number, then x z less than y z. If x greater than y, you can multiply by x. So, okay, here you get 1, over there you again get 1 is strictly greater than is a contradiction. Thus we must have x inverse less than y inverse. That's okay. Another application is that the laws of exponentiation that were previously proven for rationals are also true for reals. See section 5.6, he says, we have already seen that the formal limit of positive rationals need not be positive. It could be 0 as the example that one. However, the formal limit of non-zero, non-negative rationals that are either positive or 0 is non-negative. That's a good one. The non-negative reals are closed. I mean, in the sense, let A1, A2, A and be a whole sequence of non-negative rational numbers, then formal limit of A is a non-negative real number. But you can, if it is positive, you cannot say so, but for non-negative reals, this is true. Eventually we will see a better explanation of this fact. The set of non-negative reals is closed these days, whereas the set of positive reals is open. I don't know if it is a good way to say this. Open and closed have different meanings. So he says we argue by contradiction. No? So what are we going to prove? We are going to prove that set of non-negative reals are, and that set is closed. We argue by contradiction, and suppose that I guess this proof I went through is simple. Did you go through? Oh, I can read it now.
It's better if you read it.
Okay. We argue by contradiction, and suppose that the real number x, formal limit of the sequence A, is a negative number. Then by definition of negative real number, we have x equals limit Bn for some sequence Bn which is negatively bounded away from 0. That is, there is a negative rational minus c less than 0 such that Bn less than or equal to minus c for all n. On the other hand, we have a n greater than equal to 0 for all n greater than equal to 1 by hypothesis. That's what we are given. I'm a little bit confused. This is present open. We have to be careful. They can try to rule us. He says we are going to do the non-negative reals are closed. Let A and B a sequence of non-negative rationals. Then the formal limit is non-negative. Eventually we will be able to explain it. So we are given, then suppose that the real number x, formal limit of a, is a negative number. So what is this a? A n is a cosequence of non-negative rational numbers. Now you have the formal limit, all the an's are non-negative. He is assuming formal limit is taking x formal limit. Then what he says is true, then but the definition of negative real number, because it is if it is negative by the definition, there is a sequence Bn for some Bn which is negatively bounded away from 0. That is, there is a negative rational number minus c less than 0 such that Bn less than or equal to minus c for all n greater than or equal to 1. On the other hand, we have a n greater than or equal to 0 for all n greater than or equal to 1. By hypothesis, the numbers a n and b n are never c by 2 close, since c by 2 less than c is incorrect. Bn are, all of them are less than or equal to minus c. What we know is a n greater than or equal to 0. Then he says numbers a n and b n are never c by 2 close.
Yeah.
That is
C gap.
actually C gap. You are right. The sequences a and b n are not eventually c by 2 close, since c by 2 greater than 0 of course. This implies that a n and b n are not equivalent, but this contradicts the fact that both these sequences have x as their limit. So that's a good proof. It's correct. 5.4.10 corollary. Let a n and b n be cosequences of rationals such that a greater than or equal to b n for all n greater than or equal to 1. Then formal limits are greater than or equal. Apply proposition 5.4.9 which is to the sequence a n minus b n. I get it is straightforward.
Sir, what's the meaning of corollary?
Corollary. Meaning of corollary. Meaning of corollary is a good question by the way. When you prove a theorem, not a very major result, but simple result comes from that. No, when he is, what we proved those Proposition 5.9, where am I? Proposition 5.9. After proving proposition 5.9, if he writes a corollary, so that corollary is not as important as the previous theorem, but it is a consequence of the previous theorem, little result. That is the meaning of corollary. Lemma, actually the proposition, lemma, corollary, theorem, all of them are theorems. But when you say theorem, it's major result. When you say a proposition, it's a theorem which will be used to prove a major theorem. When you say a lemma, lemma is not as good as proposition. Lemma is something you use to prove the proposition, then you use the proposition to prove the theorem. Then corollary is a result of theorem. That is the meaning. It's a good question you ask. However, this is political. You know why? Say, you can argue with me also for this. I write a book, I say this is lemma, this is proposition, this is theorem, this is corollary. For corollary you won't argue with me. But you can say, sir, why do you say this is a lemma? This is a major result. Do you see what I'm saying?
Yeah, it's
So
it's subjective.
it's subjective, not an objective. Note that the above corollary does not work if the greater than or equal signs are replaced by greater than. He is saying if an greater than or equal to bn, then limit of an greater than or equal to, here actually is proving for formal limit. In analysis, an greater than or equal to bn, then limit of an, if the limits exist. These are Cauchy sequences, no? So there are limits for sure. If an greater than or equal to bn, then limit of an greater than or equal to limit of bn. But if you had an greater than bn, then you cannot say limit of an greater than limit of bn. Get the point, no? You? So that's why he has two examples. An is 1 plus 1 over n, bn is 1 minus 1 over n. Certainly an is strictly greater than bn for any n, but the limit of an and the limit of bn both are equal to 1. So you cannot say with the greater than, still greater than sign, you cannot conclude that corollary. We now define distance dxy. Dxy is mod of x minus y, just as we did for the rationals. In fact, proposition 4.3.3 and 4.3.7, I cannot remember what they are. Can you remember? Whole, not only for the rationals, but when I go through the book at home, I go back to pages and check. Spirit, I eat some. I have at home ratakaju. So I eat some of them.
In some books there are links to that. The number is a link in some books.
Yeah.
When we touch it, we go to the page.
Whole not only for the rationals, but for the reals. The proof is identical since the real numbers obey all the laws of algebra and order that the rationals do. We now observe that while positive real numbers can be arbitrarily large or small, they cannot be larger than all of the positive integers or smaller than in magnitude, smaller in magnitude than all of the positive rationals. So this is again an important result as far as analysis is concerned. So as a result, let's treat it. Doesn't matter, no? It's not difficult, but because it is an important one for us. Let x be a positive real number, then there exists a positive rational number q, such that q less than or equal to x. So this is very important. But it says is, you get the, I mean, these are trivial as far as we are concerned. But when you are going to do maths, when you write a proof, you cannot say you cannot write what you think. Of course you write what you think, but they must be true. May be able to justify or prove or verify. Here he says, let x be a positive. So 0 is here, x is here. Let x be a positive real number. Then there it is the positive rational q, such that q less than or equal to it. What he is saying is, there is a rational number here. If you take any positive real number, there is a rational number in between 0 and the given positive rational. I mean, of course it is true, but we need to prove. And the next one is again important. There it is supposed to be integer capital N such that x less than or equal to capital N. So, of course, indirectly capital N is also a rational. N is rational. But the thing is, you cannot say there is a positive integer smaller than x. You cannot say that. Here there is a positive integer. Very important. So because it is an important one for us, let's go through the proof. Since x is a positive real, it is the formal limit of some Cauchy sequence which is positively bounded away from 0. Right, no? Also by lemma 5.1.15, lemma this sequence is bounded. So I get, for you it is important results, Cauchy sequences are bounded. That you need to keep in mind. And you must be able to prove it also. Not now, but you know. Thus we have rationals q greater than 0 and r such that q less than or equal to a n less than or equal to r for a n greater than or equal to 1. Since when we say a n is bounded, I wrote it clearly. A n's are bounded, that means there is a lower bound somewhere here and there is an upper bound somewhere here. Now in since x is vector, it is bounded formally for Cauchy sequence A. These A's must be rational, yes, etc. No? That's why I got the difference there. Since x is a positive real, it is the formal limit of some Cauchy sequence a n and going on to infinity of rational numbers, no? Which is bounded away from. Sometimes he emphasizes, I don't know, when he wants to emphasize, he emphasizes. So we have to go through it. Also by lemma, this sequence is, when you say bounded, from either side there are bounds. A n greater than this number, any a n less than this number. So according to the definitions you had earlier, this upper bound as well as lower bound both must be rational. But when you study analysis, they don't have to be rational. If you say a sequence is bounded, I say the sequence A n is bounded. What does it mean is all the terms of the sequence A n are in between some two real numbers. That's all. Here in this case in between some two rational numbers. That's all. But by proportion 4.4.1 we know that there is some integer capital N such that r less than or equal to a. So I cannot remember that.
The Archimedean thing.
Yeah. 4.4.1. Since q is positive and q less than or equal to r less than or equal to n, we see that n is positive. Q positive, no, so r less than or equal to n, q less than or equal to r, etc. So n is positive. Thus q less than or equal to an, strictly less than capital N, for all n greater than or equal to 1. Applying corollary 5.4.10, because since the ends are in between q and n, formal limit also must be less than in between q and n, right? Because what? Just before a while we proved that if an less than or equal to bn, formal limits maintain the same order. Strictly less than, it doesn't work with strict inequality. Less than or equal to. So this is a very important result, however. You need to remember. What happens is, even if you become an expert, sometimes you may not be able to do very little things. It can happen very easily because you are concerned about big theorems, big results. Somebody comes and say, okay, prove that given any x, there is a smaller given bigger integer capital N. Again, the way you write the proof is different. Now this proof work is his definitions. He has different axioms, this and that. He says he has said no that they will not be in other books. So if you ask me to do this after the class is over, not today's class, this lecture series is over, I may give a completely different proof. Here, in a way, I noticed that his method is, if you can remember all this, certain results can be proved very easily by his method. Yeah, I noticed that. So if you real number system construction is, if you really get it, if it goes to your blood, it is good. Many results by his style, easy to prove. But the thing is, if you tell this thing to another person, he may not understand. We understand now because we have been through his book, no? And Archimedean property comes. Archimedean property. Let x and epsilon be any positive. Did we go through this before?
Yeah, I think so.
So are we? I can't remember it.
Yeah, even I just remember talking about this.
Yeah, we discussed this now. So maybe we have gone back. I said this is also given into real numbers, x less than y, we can find it. We discussed this now.
Yeah, I just
This is also an important one. I told you the other day, also given any two real numbers x less than y, we can find a rational number q, such that between any two real numbers there is one rational. I was saying if there is one rational, there are infinite many rationals. Again, I discussed about even there will be one irrational. We discussed how to prove it. No?
Yeah.
So we have, I guess, doesn't matter we are talking. Let's see whether I think we have finished this. No? This is an important exercise. 5.4.3. Show that every real number x there is exactly one integer capital N. Exactly one. Such that capital N less than or equal to x and x strictly less than n plus 1. This integer capital N is called the integer part of x and is sometimes denoted by n. That has a name. Some students know it, I don't know. Anyway, what I am saying is this result is important. But you know it. But it's important in the sense if you know how to do it, that's a good one. The next exercise is also an important exercise. In analysis, show that any positive real number x greater than 0, there is an integer such that x greater than 1 over n. I mean the proof is trivial, no? When you are given x, n, Sorry, when you are given x, you can find an integer n such that n greater than 1 over x. So that's the solution. Archimedean property. So we have discussed this in the material. Next exercises are also important. You need to do them very carefully. If you get stuck, by any chance if you cannot do, or the one who is grading has not convinced you what you want, then we should come back and do it. Least upper bound property. Did we discuss that also? Upper bound, I remember. Because I cannot remember what I taught you. You know, I go through this several times at home. As a result, maybe I should have a pencil to put a check that we came that far. Anyway, even if we have done this thing, let's go through because this is very important in analysis. The least upper bound property. We now give one of the most basic advantages of the real numbers. We read, I remember I was reading it over the rationals. One can take the least upper bound, sup t, I talk about, so it's not, the sup is not the one we had at Mount Lavinia Hotel. Sup e of any subset, capital E of the real numbers. Let E be a subset of R and let M be a real number. We say that capital M is an upper bound for E if and only if we have x less than or equal to M for every element x in E. That is understood, no? If you want to say capital M is an upper bound, you have a set, you have
It's blue and plus
blue one, this one,
the other.
this one. You have the real line. What it says is, let E be a subset of R and let capital M be a real number. We say that capital M is an upper bound for E if and only we have the set here E. Let's say set E is this part, something. If you want to say capital M is an upper bound, capital M must be E. If set is left of the number capital M. That is the meaning of upper bound. Example, if you take this set, 0 less than or equal to x less than or equal to 1, of course 1 is an upper bound. The difference here is, however, 1 is also in the set. However, then 1 is an upper bound for E since every element of E is less than or equal to 1. It is also true that 2 is an upper bound for E, and indeed every number greater than or equal to 1 is an upper bound for E. On the other hand, any number less such as 0.5 is not an upper bound for upper bound because 0.5 is not larger than every element in E. That is wrong. We discussed this. Anyway, so even repeating the same thing for this kind of results is not logical thing is very lousy, logicalness. Let R plus denote the set of positive reals, then R plus does not have any upper bound at all. Why? You have the real line. You have 0 here. All the numbers going all the way. It does not have an upper bound. How do we know?
Can you see the Archimedean theorem?
No. Archimedean is coming. The way to remember about Archimedean property is that given any real number x, you have a bigger integer. That's what it says, positive integer.
So we can
Indirectly, you can say, if you want. His question is whether we can use the Archimedean property, but we don't use Archimedean property for this.
This contradiction.
I mean, so, I mean, the set of his question has maybe something. Let R plus the set of reals, then R plus does not have any upper bound at all. So what is your proof anyway if you are using Archimedean property?
For every positive real number, there exists a larger integer, positive integer n by Archimedean theorem. So for all R plus, there exists n such that R for x in R plus n is always greater than x.
Made. My wife, they call it Mrs. Ramsey, because I am Ramsey. Then by Archimedean property, you get x, there is an integer, positive integer greater than x. So let's denote it by nx. Nx greater than capital X. Now what you are saying is, our set is R plus. Set of all x belongs to R such that x greater than 0. That is our set. So what you said goes, for each x here, there is a bigger integer, nx. I mean, if you take the real line, here is 0. For this x, there is somewhere, if this is x, you have nx. If this is y, you have somewhere in y. But what we want is, we want to say that there is no real number. Now, you cannot take nx, ny, and if you take z for instance, then you have nz. But you are not getting a bound for all of x. Now, if you have 2-3 members in the family, you go to your mother, if you have 3 members, you are a handsome guy, other people may not be that handsome, so let me so, say suppose your mother is your mother with the nice hair, like that. So you call my mom, this person calls my mom, this person calls my mom. Like that here, I have to have a number, one number bigger than all the real numbers. Here you are saying, if you take any x, there is a bigger integer.
But if we mention that nx is also is an element of R plus, then is the proof correct?
No.
N is also a real number.
Yeah, then n is also real. Again, he has upper bound, so it endlessly.
That type of is about ordinals.
Okay.
Yeah, ordinals is such a thing.
Best way is contradiction, right?
Best method is to go by proof by contradiction. Best method. Sure. Can you do it by proof by contradiction? Then let's go through. I will go. Suppose R plus is bounded above, sorry. Then you have some real number capital N with the property that for every x belongs to R plus, x less than or equal to capital N. Now, if you take m plus 1, it's a real number. So you say, therefore m plus 1 less than or equal to m. Contradiction. Understand? Okay, let's go. Why? We answered why. Example. I told you this is not the way to write the empty set. Keep in mind that. Let empty set be the empty set. Then every number capital M is an upper bound for empty set. Because capital M is greater than every element of the empty set. This is vacuously true. What he says is you take the empty set, every number capital M is an upper bound.
M should be non-negative.
I'm sorry, Buddha, I didn't get what you said.
M should be non-negative.
No. No. You have the empty set. He is saying empty set does not have anything. No? So, if one can say for every x belongs to empty set, that is false.
It's not 0. If it was 0, M should be
No, I mean M can be negative.
yeah.
Yeah. I mean, now we are not in example 5.5.3, we are over with it. Now we are looking at the empty set. Upper bounds can be negative, no problem at all. For instance, if you take the set of all real numbers is strictly less than -3, then -2 is an upper bound of that set. No?
Oh, yeah.
It can be. But here he is saying if you take the empty set, any real number is an upper bound for that set. I mean, of course, one may think that wasting time is so nonsense. Since there is nothing in the empty set. He says anyway, then every number capital M is an upper bound for empty because M is greater than every element of the empty set. This is vacuously true statement, but it's still true, he is saying. It is clear that if M is an upper bound of E, then any larger number M less than greater than or equal to M is also an upper bound of E. No? It's clear. On the other hand, it is not so clear whether it is possible for any number smaller than capital M to also be an upper bound of E. I think this motivates the following definition. I don't know. I did not like that paragraph, but let's go on. Definition 5.5.5. Least upper bound, very important word in analysis. Let E be a subset of R and capital M be a real number. We say that capital M is a least upper bound for E if and only if M is an upper bound for E and also any other upper bound M dash for E must be larger than or equal to M. This is not how I write, however, but let's go on. Because when you to say, what he is saying is, if capital M is a least upper bound, that is means smallest upper bound, then if you take any other upper bound, it must be greater than or equal to this one. That's what he is saying. Let capital E be the interval set of all x in between 0 and 1, including both of them. Then, as noted before, E has many upper bounds. Indeed, every number greater than or equal to 1 is an upper bound. No? But only 1 is the least upper bound. All the upper bounds are larger than 1. So, now, can we prove this thing? Of course, it goes without saying, but if you take the set of all reals between 0 and 1, including both of them, of course 1 is an upper bound. But can you say 1 is the least upper bound? But only 1 is the least upper bound. I mean, for discussion, it is true, but to write a proof, there is something. Think about it. I'm not going to go to it now. Let's see if I can say the empty set does not have a least upper bound. Because since every real number is an upper bound, you take m by 2 is again an upper bound, no? If m is positive. Otherwise m minus 1 is certainly less than m. So we answered that why. Now, uniqueness of least upper bound. That is very important. I want to tell you, I have told this to you earlier. In other people's constructions of real number system, every non-empty subset of R that is bounded above has a least upper bound. It is an axiom. It is called completeness axiom. Here in this case, in his book he is proving. So it is completely different. So that's why I am wondering sometimes, when it comes to basics, whether you will have trouble with other people, because you know what I am saying? Uniqueness of least upper bound, but that is, let's go through, that's true, you can understand, but I want to go through. Let E be a subset of R, then E can have at most one least upper bound. He is not saying he has an upper bound. If there is only one. Let capital M1 and capital M2 be two least upper bounds. Say M1 and M2. Since M1 is a least upper bound and M2 is an upper bound, by definition of least upper bound, M2 greater than or equal to M1. Why? Because M1 is an upper bound, M1 is the least upper bound, capital M2 is an upper bound, therefore M2 must be greater than or equal to M1. Other way is also true. If you say, since capital M2 is an upper bound, since capital M2 is a least upper bound and M1 is an upper bound, we have M1 greater than or equal to M2. Understand? No? But this kind of arguments come in analysis a lot when you are growing the uniqueness. When you are growing the uniqueness. Thus M1 equals M2. Thus there is at most one least upper bound. Now we come to an important property of the real numbers. Existence of least upper bound. I am very uncomfortable. He is saying, if he is an unempty subset of R, then he has an upper bound. Then it must have exactly one least upper bound. What he is going to prove is that if he has an upper bound, then it has to have a unique least upper bound. We know the uniqueness part already, but he is going to prove. He himself says this theorem will take quite a bit of effort to prove. Because for me it is an axiom. And many of the steps will be left as exercises. That's also, even if he cannot prove, not for me. Some other people do this thing. Yeah, because when he cannot, the lecturer cannot do it, he says, oh, it's easy to show that. He cannot do it. Okay, anyway, as I told you, now for instance you are thinking of going to Colombo University, I don't know, in my time they were introduced. If the real number system is introduced, they will say 10 axioms, 10th one is that, completeness axiom. Every non-empty subset of R which is bounded above, that means one has at least one upper bound, has a least upper bound in R. Least upper bound is also the real number. Now in his case he is going to prove it. So because he has done many things assuming principle of mathematical induction. So I don't know one other thing, that how he is going to go to talk about numbers. I don't know whether it is because it is an analysis book, he may not do it, but I'm wondering. This theorem will take quite a bit effort to prove, and many of the steps will be left as exercises. Thank you. Let capital E be an unempty subset of R with an upper bound M. By proposition 5.5.8, we know that he has at most one least upper bound. That we know. We have to show that E has at least one least upper bound. Since E is non-empty, we can choose some element x0 in S. Right? He has proved previous theorem, if a set has a least upper bound, at most one. Now he is going to prove at least one, then it is unique. Then theorem will be every non-empty subset of R that is bounded above has a unique least upper bound. Now let's see, since he is non-empty, we can choose some element x0 in V. Did you go through this proof? No. You? No. Okay. Let n greater than or equal to 1 be a positive integer. We know that he has an upper bound capital M. By the Archimedean property, we can find an integer capital K such that K by n greater than or equal to M. Right now? Because Archimedean property, this way also you can write, according to our style, you can say there is an integer K such that K greater than or equal to Mn. Because Mn is also a real number. So somehow it is written this way, doesn't matter. And hence K by n is also an upper bound for E. Now this n is arbitrary. Let n be a positive integer, anything. Capital K depends on n. It's like a capital K subscript n, if you were to be precise. And hence K by n is also an upper bound of it. By the Archimedean property again, there exists another integer L, such that L over n less than x0. How can you prove that? I proved it at home. I cannot remember now. How did I do it? Can you prove it? Because Archimedean property always says, given a real number, there is a bigger integer. Now it is going to go backwards. How can you prove it? I proved it at home. I cannot remember. That's the thing. Can I recall? Maybe he would prove, so he doesn't. No, it's not fair by the Archimedean property. Again, there exists another integer L. That's that. Can you prove it using Archimedean property? How can you prove it? Can you? I did this one now. L over n less than x equal. This means A is growing. Is this correct? N is a given integer. X0 is a real number. However, this one is an integer, be careful. Over there, we can find this case, Archimedean property talks about positive integers, no? But I get confused with things.
No, like since x naught is real number, x naught can be negative, no? So
Yeah.
L can be negative as well.
Yeah, of course. Even over there, according to him, he also can be, I mean, it is the way written integer, no, but it is a positive integer, no, Archimedean property. Archimedean property says, then there is a positive integer n. Now, how can we prove this thing? Nx0 is a, it can be negative also. How do we know there is an integer L less than n is 0? How? Because Archimedean property is about having a positive real number. Sorry, positive integer greater than the given real number. Here he is saying again by the Archimedean property again. How can we do it? Do you have any idea? I think pictures are good, no? If you take minus nx0, this pen also not good to that. Minus nx0 is a real number. By the Archimedean property, there is some integer. I don't know. Minus nx0, by Archimedean property, there is a bigger positive integer. So, I will say again, capital N. Capital N is positive. However, then we don't need Archimedean property. No? Positive numbers are greater than any negative numbers in the way, but I don't know whether or not this is negative, though there is a negative sign. Now, from this is a positive integer somehow by Archimedean property. Then you get minus n is strictly less than nx0. Right? So then I will put in the place of minus m, I will say L. L is an integer less than nx0. So therefore L over n less than x0. No, that's how we did not know, right? No? Okay, so however, he should have, so we can find out, he should have said that we can find a positive integer k, since he is using Archimedean property. Okay, anyway now, k by n greater than or equal to m, k by n is in the upper bound. Now, L over n is less than x0, x0 is a member of E. We see that L over n is not an upper bound for E. L over n less than x0, no, but it cannot be an upper bound for E. We see that L over n is not an upper bound for E. Since k over n is an upper bound, but L over n is not an upper bound, k greater than or equal to n. Why? K by n is an upper bound, L over n is not an upper bound. We see that k greater than or equal to n. L, sorry. Why?
Because k over n is greater than L over n and n cancels out because n is a positive integer.
K over n, how it comes is, why do you say k over n greater than or equal to L over n?
Because
X0.
x0 is less than k over n.
Yeah. Like this way, no? K over, right? Then you can multiply by what? N. Anyway, so we see that k greater than or equal to L. since k by n is an upper bound for E and L over n is not, we can find an integer mn. Lies between L and K with the property that mn over n is an upper bound for E. Can we convince that? He said no. Quite a bit of effort to prove. I went through this thing, but somehow I didn't like it that much. Anyway, can we see now we have k greater than or equal to L. We have, in fact, we can say k is strictly greater than L, no? Because here L by L less than x0. L by N is strictly less than x0. Anyway, now let's say, can we get it that since k over n is an upper bound for E and L over n is not, we can find an integer mn in between L and K, that side could be equal. How do we know that?
mn is a real number.
No, mn is an integer. No?
Yeah, then
We can find an integer capital. We can find an integer he meant for mn. How do we know? He says since k by n is an upper bound for E and L by n is not, we can find an integer mn in between L and K. How do we know?
L and K are real numbers now, so you can find another real number in between L and K.
Mn is an integer. We can find an integer. That's why I'm asking how do we know that? How can we do? So actually here or there he is using the fact that L is strictly less than K. Otherwise, how can he write here L less than mn? How do we know that? How do we know? L is an integer, though he has not written k is a positive integer. L can be positive, negative, whatever, we don't know about that. K is definitely positive. Now,
K is actually strictly greater than L.
how about you? When you are going to prove it, since k by n is an upper bound, and E is of A and L over n is not, you have to use that.
Okay.
Otherwise, you cannot prove it. So I guess he has jumped. We have k by n. Here you have L by n. Here you have k by n. This guy is an upper bound. No, this guy is not an upper bound. What does it say?
so the thing when you simplify you get capital L is less than k, strictly less than k. We know that since L and K are both integers, L is strictly less than L plus 1.
Definitely.
And since L is less than K, L plus 1 is less than or equal to K.
You are saying like that. L less than or equal, no, sorry, maybe t time. L is less than L plus 1. Oh, L plus 1 less than or equal to K, that's what we are saying.
Yeah.
My question is not that. Since K by N is an upper bound for E and L by L over N is not, where do you use that?
So when the upper paragraph it says since K by N is an upper bound and L is not, we can see that K is greater than or equal to N, so using that data.
No, what I am asking is something else. This paragraph begins, since K by N is an upper bound for E and L by N is not, we can find like this, he says. Where do you, when you are writing this, L plus 1 less than or equal to K, where did you use the fact that?
From the starting point, K is greater than. So that since K is
You are saying a general fact, if L less than K, then L plus 1 less than or equal to K. That's what you are saying. It has nothing to do with K by N is an upper bound for E and L by N is not. අපි දෙකක් දීලා ඉඳමුද? So anyway,